So look at this problem. We have a function here in time, e to the power minus absolute value of tau over square root of 2 sine, let's say absolute value of 2 t square root of. So it's a complicated function plus some phi. Question is, whatever you see here, is this an autocorrelation or not? So it's difficult to answer yes or no by just looking at it. So easiest way is find the power spectrum and see whether it's positive or not, or for what values of for phi. So find out the conditions on phi. So that's what we are going to do. For power spectrum is of course the transform of the autocorrelation some function. So the idea is if this is an autocorrelation function, then the transform would be positive, right? R tau e raised to minus j omega tau. So basically it's a problem on doing power spectrum or Fourier, finding Fourier transform. So I'll just do it. No big deal if you know how to do it. And the big deal is only if you don't know how to solve, do such problems to figure it out. So you need some skill. So let's see how this goes. So this is tau also, just one variable, tau over square root of 2 plus phi e to the power minus j omega tau d tau. So I'm going to, first of all, you can see this whole thing is an even function, and this is even plus odd. So because I can write this as cos omega tau minus j sine omega tau. Sine omega tau is odd, this is even. So even multiplied by even is even. Even multiplied by odd over a symmetric region is 0. So this integral becomes just the integral over the cosine part. So that's the first break. E raised to minus tau over square root of 2 sine tau over square root of 2 plus phi cos omega t d tau d tau. So we need to do this. Again, there is another break here because this is an even function over a symmetric interval. So this is 2 times the integral from 0 to t. So sxx omega becomes 2 times the integral from 0 to infinity, e raised to minus tau. Now I don't need the absolute value because everything is positive. So tau over 2 sine tau over square root of 2 plus phi cos omega tau d tau. Okay, so we bring it to this stage. And now I'm going to use sine A sine B to, so 2 sine A sine B is sine A plus B plus sine A minus B. So this expression becomes 0 to infinity e raised to minus tau over square root of 2 sine A plus B. So that becomes 1 over square root of 2 plus omega multiplied by tau plus phi. So that's a sine A plus B plus sine A minus B. So basically same thing with the minus here. So 1 over square root minus omega tau plus phi. So this integral needs to be replaced. So to do this, simply think of sine as the imaginary part of an exponent. So we can combine this with and do this. So this is obviously the imaginary part of e to the power j, and we have a e raised to minus. So I'm going to write it one at a time. So this is 0 to infinity e raised to minus tau over square root of 2. And this is going to be the imaginary part of e to the power j, this quantity, 1 over square root of 2 plus omega tau plus phi plus e to the power j 1 over square root of 2 minus omega tau plus phi, whole thing multiplied by d tau. So I'm going to combine with this. So this becomes, and remember the derivative is, the integral is only on t, not the phi. And because of the exponent, I can pull out the exponent, I can combine these two together. So if you follow me, you can see that this is integral 0 to infinity. And e raised to minus 1 over square root of t from 1 over square root of 2 from here. Then you have, because I took a minus outside, this is minus j 1 over square root of 2 plus omega multiplied by tau. Oh, plus the same thing with a minus sign here. So e raised to minus 1 over square root of 2 minus j 1 over square root of 2 minus omega tau. And there is a e raised to j phi on both, so I can pull it outside here, but still within this imaginary argument. So this whole thing d tau. So now you have two integrals, each integral is easy. So this is going to be, we just need to simplify e raised to j phi, then notice that this is e raised to a complex number with the real part positive. So when you integrate, you get 1 over this quantity with a minus sign. But the top limit is 0 because e raised to minus infinity divided by square root of 2. So that goes to 0. And the bottom limit is e raised to 0, 1. So this becomes 1 over just the constant. So 1 over square root of 2 minus j 1 over square root of 2 plus omega plus 1 over square root of 2 minus j 1 over square root of 2 minus omega. So essentially the problem is just to completing this. So I'm going to multiply by the complex, many ways you can do this. Let me multiply by the complex conjugate squared on the numerator of each. So that becomes, so sxx omega becomes imaginary part of e raised to j phi, and then 1 over square root of 2 plus j 1 over square root of 2 plus omega, and this becomes the square of the, so we get the square of this, which is half plus this quantity squared. So that's half plus 1 over square root of 2 plus omega squared. And basically here you get the same thing with a minus for the omega plus j 1 over square root of 2 minus omega divided by half plus. So this is going to be, if you expand the denominator, you see half plus half is 1. So let me simplify this a little more. So it's imaginary part of j phi. Then you have just repeating the numerator here, 1 plus square root of 2 omega plus omega squared. Here you have 1 minus square root of 2 omega plus omega squared, and this is half plus j 1 over square root of 2 minus omega. So if I cross multiply, I get imaginary part e raised to j phi. So 1 plus omega squared plus this, 1 plus omega squared minus this. So the denominator comes out to be 1 plus omega squared minus square root of 2 omega, the whole square. And here I will cross multiply, let's see, plus j square root of half plus omega, 1 minus 2 omega, square root of 2 omega plus omega squared plus square root of half plus j 1 plus square root of 2 omega plus omega squared. So this needs to be simplified. Uh, so if you write this up, let me just do it here, one more step. So e raised to j phi, the denominator is ec, because that's, if you expand this, you get 1 plus omega squared, omega 4 plus 2 omega squared minus 2 omega squared. So this denominator simply becomes 1 plus omega 4. And the numerator is so notice that here it should have been square root of 2. So that comes out to be, if you collect all the terms, you have one. Let me just write it down. So this is 1 over square root of 2. I see 1 plus omega squared here, and I also see 1 plus omega squared twice. So multiplied by twice. That's basically the and the square root of 2 minus 2 square root of omega cancels with this one. So this is basically the real part, plus j multiplied by this multiplied by this. So that's going to be half multiplied by 1 over square root of 2 plus omega plus so from here and from here, and then plus half minus omega squared multiplied by 1 over square root of 2 twice. So let me simplify this into the next page. So this gives us sxx omega equal to imaginary part of e raised to j phi square root of 2 multiplied by 1 plus omega squared plus j multiplied by 1 plus 1. So if you simplify the previous terms, it will simply turn out to be 1 minus omega squared multiplied by square root of 2 and 1 plus omega 4 here. So if I pull out all the, so this is square root of 2, then you have cos phi plus j sine phi multiplied by, so still the imaginary part of this multiplied by 1 plus omega squared plus j 1 minus omega squared over 1 plus omega 4. So that will be cos phi multiplied by this. So I'm just going to write the answer. Cos phi multiplied by 1 minus omega squared plus sine phi multiplied by 1 plus omega squared divided by 1 plus omega 4. So if you want, we can write this as square root of 2 by pulling out the cos phi outside as 1 minus omega squared plus 1 plus omega squared multiplied by tan phi over 1 plus omega 4. And this further you can simplify as omega 2 multiplied by cos phi. Notice you have here you have 1 plus tan phi, because phi is the tricky one, plus tan phi minus 1 multiplied by omega squared divided by 1 plus omega 4. So we want this to be positive. That's the whole point. So we can see the conditions on this. So certainly we want this to be positive. That means phi should be greater than pi by 4. During that region, this is positive also. So phi should be between pi by 4 and less than pi by 2. So I guess that's the answer of conditions on. So going back to the original problem, then this will be positive. So the r of tau, which is e raised to minus tau over square root of t sine, this complicated function will be an autocorrelation function for tau for phi greater than pi by 4 and less than pi by 2. The whole point is then the power spectrum, corresponding power spectrum will be non-negative. So that's the way, that's one way to check whether a given time function is an autocorrelation function or not.